Let's start. Today we're gonna talk about the linear independence. Before starting, let's recap what we have learned in the last week. We were talking about the solution set of the linear system, right? So we were talking about the homogeneous linear system. The homogeneous linear system means like the AX equals B, right? So for example, if we have the linear system, something like this, so we were dealing with some kind of AX equals B formulation. However, in the homogeneous linear system, we were talking about the B vector B is equal to 0. So this is the kind of the AX equals 0, right? So this is the homogeneous linear system. So yeah, there was the solution for the homogeneous linear system like that. And here, yeah, and we were talking about the parametric vector form with the homogeneous solution or the AX equals B system, right? So the parametric vector equation of the solution looks like that. So vector x is equal to scalar s times the vector u plus the scalar t times vector v, right? So there is the way to write the solution set of the consistent system in a parametric vector form. So first of all, we have to reduce the augmented matrix to the reduced echelon form, or called the REF form, right? Then then express each basic variable in terms of the any free variable, right? So this is the parametric solution of the system, and then write the typical solution x as a vector whose entry depends on the free variable, and then decompose x into the linear combination of the vector using free variable as a parameter. So why we have to deal with the homogeneous system? Because if we want to solve this non-homogeneous system such that AX equals B, then there is the corresponding homogeneous system AX equals A if this matrix A is same, right? Then let's say the solution of the AX equals B as a X non-homogeneous, and let's say the solution of the homogeneous system as a X homogeneous, something like this. Then the non-homogeneous system solution can be represented in terms of the arbitrary vector u plus the scalar times the non-homogeneous solution, right? So geometrically, it means that symmetry means that, okay, if we want to solve the AX equals B, and if we already know the solution of the AX equals 0, then we can just find this solution by just shift from the solution of the AX equals 0. So this is the solution of the non-homogeneous system, okay? In the three-dimensional space, that the solution of the AX equals B will be the plane, and AX equals 0, the homogeneous system, will be also plane. But in this case, these two planes are parallel. The AX equals solution of the AX equals B is just the shift version of the solutions of AX equals 0. So yeah, there is a relationship between the homogeneous and non-homogeneous system. Okay, so it was the last week. Then in this week, we want to introduce some concept called the linear independence. Okay, what is the linear independence? Here is the definition. Okay, if there is an indexed set of the vector, let's say V1, V2 through the Vp in the Rn space, it means that the, for example, vector V have some kinds of entry, something like the 1, 2 through the V I comma n. So what does it mean? So the size of this vector is the n times 1. So n means that there is the n row, right? And then there is just one column. So this is the definition of the vector vi in Rn space, right? So anyway, so a set of vector v1 through the vp in Rn is said to be the linear independence if the vector equation, like the x1 times v1 through plus x2 times v2 through the xp times vt is equal to 0, has the only trivial solution. Only trivial solution. What does it mean? Okay, in the until last week, we were talking about the ax equals b and non-homogeneous non-homogeneous system ax equals b and homogeneous system ax equals 0, right? So it was homogeneous system. Then let's say the matrix A looks like that. So then size of the matrix A is m times n. What does it mean? There is the m equation with the n variable, right? So this is the definition of the matrix A. Then we can represent this matrix A as a column vector of the matrix A. Let's say the matrix column vector A1, A2 through the AN, right? So what does it mean? So column vector A1 of the matrix A is consisting of the some entries like this. So this is the column vector of the matrix A. Then what does it mean? Okay, let's say the V1, V2, VP. VPs are the column vectors of the some kind of matrix A or the some kind of matrix V, something like that. Then this vector equation can be represented in a matrix equation like the let's say V times vector x equals 0, right? When V is represented by V1, V2 through the VP, right? So what does it mean? So this vector equation is the homogeneous system. Homogeneous system of the vector x, right? So if you remember what is the homogeneous system, there are two kinds of solution, right? Let's go back to the previous lecture. Yeah. If we go back to the homogeneous linear system, there are two possibilities of the solution, right? So first one is the trivial solution when x equals 0, and another case is the non-trivial solution case when non-zero vector x if there exists a non-zero vector x that satisfies ax equals b, right? So linear independence. So linear independence means if there exists only trivial solution of the homogeneous system, we can say that those column vectors of a matrix V or A are linear independence, right? So then, what about the reverse case? What about the reverse case? We can say that the set V1 through the Vp is to be the linearly dependent if there exists the weight C1 through the Cp. Of course, those values are not all zeros, such that C1 times V1 plus C2 times V2 through the Cp times Vp is equal to 0. So what does it mean? So let's say, okay, we have a vector, a matrix V with some kinds of the vector x, and when we solved this homogeneous system, we found some kinds of the vector, let's say the C1, C2 times Cp, something like that. Then there exists, and then C1 non-zero or C2 non-zero, something like that. So in this case, there exists a non-trivial solution of the homogeneous system, right? So in this case, the column vectors of the matrix V is said to be the linearly dependent case, right? Okay. So comparing to the linear linear dependent means that there exists the non-trivial solution of the homogeneous system. Okay. So it is also called the linear dependence relationship, this equation, among the vector V1 through the Vp when the weights are not whole zero. It means there exists a non-trivial solution. Trivial solution exists. So in other words, the indexed set is linearly dependent if and only if it is not linearly independent. Of course, yes, right? Because the so linear dependent and linearly independent are to say the in the reverse relationship. Okay, so this is the definition of the linear independence. Okay. And then why we have to learn the linear independence? Because, okay, let's see the example. Okay, here are three kinds of the vector v1, v2, v3. v1 is looks like this, v2 is looks like this, and v3 is looks like this. Let's say this is this x-axis as a first elementary of the vector, and let's say this is the second elementary of the vector. Then what is the vector v1 in this figure? Looks like this, okay, right? This is v1 because this is the 1, 0, right? Then what is the v2? v2 is the 0, 1. What about v3? v3 is -1 times -2, something like that. In this case, those three vectors are linearly independent or not? Linearly independent or not? To become a linearly independent vector, something like C3 times V3 is equal to 0. We have to determine there exists a non-trivial solution of the C1, C2, C3 or not, right? So what does it mean? In this case, vector V3 can be represented represent in terms of the V2 and V1. How? Okay, if we compute the negative V1 here, looks like this, and compute the negative V2, looks like this, and then if we add the negative V1 plus negative V2, we'll make the vector V3. In other words, V3 can be represented as a negative V1 plus negative V2, right? So in this case, V1 plus V2 plus V3 is equal to 0. So in this case, there is the solution of the 1, 1, 1, right? So it means that there is a non-trivial solution. So those vectors are linearly dependent. Those vectors are having linearly dependent relationship. Okay, so what does it mean? V3 vector can be represented by the V1 and V2. It means that if we want to make some system and there exists some kind of the vector V1 and V2, actually V3 have the how to say, V3 don't have any independent role comparing to the V1 and V2, because the role of the V3 can be replaced by V1 and V2, or the linear combination of the V1 and V2. So it means that the concept of linear independence are related to the there exists no redundant vector or not. Okay, so this is the concept of linear independence. Okay, let's see the example. There exists three vector. V1 is equal to 1 to 3, V2 equals to 4, 5, 6, and V3 equals to 2, 1, 6. The first question is determine the set V1, V2, V3 is the linear independence. The second question is, if possible, please find the linear dependence relationship among the V1, V2, V3. Okay, so first of all, this system, the system that consists of these three kinds of column vectors are linear independent or not. To answer the question, first of all, we try to find the solution of those system. Okay, so first of all, so let's say the three scalar element x1, x3, x1, x2, and x3 looks like that, and with the three column vector, something like that. What was that? It looks like this, right? That in this case, let's try to find the solution of this equation. Okay, then how can we do that? First of all, we have to find the augmented matrix of the system and then row reduce those augmented matrix into the what? Echelon form of the matrix, right? Okay, so here is the vector v1, v2, v3. So in this case, this is a v1, v2, v3, right? And this is the right hand side of the linear system. Okay, so first of all, to row reduce this original matrix, okay, let's say this matrix as a V B, right? Then what can we do? First of all, we have to reduce this term, right? Then after that, we have to do same things on this sub matrix and then reduce this term, right? So this is the procedure of the row reduction algorithm. Okay. So first of all, what do you have to do? Okay, let's say this is R1, R2, and R3. Okay, so first of all, R2 should be replaced by the R2 minus 2 times R1, something like that. Okay, then we can reduce this value like this and like this. Then we can get this value, or if we recursively serve this system, we can finally get this echelon form. Please do in yourself, okay? Okay, so anyway, so from this original matrix, we have a echelon form of the matrix. Okay, what do we infer from this echelon form of the matrix? Because this is the pivot position, right? Pivot position. So this is the pivot column, right? It means that x1 and x2 are basic variable and x3 are free variable, right? So x2 and x2 are basic variable and x3 are free variable. So what does it mean? Each non-zero values of the x determine the non-trivial solution. In other words, the non-zero values of the x3 determines the x1 and x2, right? So therefore, V1 and V2 and V3 are linearly dependent because there exists a non-trivial solution x1 and x2 and x3, right? Non-trivial solution. So this is a case of linearly independent. Okay. So the second question was that if possible, please find the linear dependent relationship among the vectors. Okay. So to find the linear dependent relationship, what was that? The vector equation of the V1 and V2 and 3, V1 and V2 and V3. So we finally find the solution of this x, right? So how can you do that? From the echelon form of the original matrix, we further row reduce the echelon form of the matrix as a row reduced echelon form of the matrix. Okay? And then if we go back to the equation form, we can get the x1 minus the 2, x3 is equal to 0, x2 plus x3 is equal to 0, and 0 is equal to 0. Then we can say that x1 is equal to 2x3, x2 is equal to negative x3, and x3 is the free variable. Then as varying the value x3, we can get the infinitely many solution of the x1 and x2 and x3, right? So let's say x3 is equal to 5, then we can say that x1 is equal to 10, x2 is equal to negative 5, right? In this case, we can represent this vector equation something like this, right? So this is the one possible linear dependence relationship among the V1 and V2 and V3, right? Of course, as varying this free variable x3, we can find so many linear dependent relationship of the V1 and V2 and V3, right? But this is one of the possible linear dependence relationship. Okay. So this is the concept of the linear independence. Okay. Now let's move on to the matrix form. Okay, so suppose that we begin with the matrix A is equal to A1, A2, and AN. This is the column vector. Okay, let column vector, right? Instead of zero vector, right? Then matrix equation AX equals 0. What was that? Homogeneous system, right? Can be written as this form, right? Why? Do you remember why? Because A times X means that A1, A2, AN times the vector X1, X2 times Xn. Because the number of column should be same as the number of row of the vector x, right? So in this case, ax equals 0 can be represented something like this. So what does it mean? Each linear dependent relation among the columns of A corresponding to the non-trivial solution of the ax equals b. We already discussed this, right? So non-trivial solution of the ax equals 0 corresponding to the linear dependent relation among the columns of the matrix A. Okay, so let's go back to the homogeneous system. There were two kinds of possibility of the solution of the homogeneous system, right? What was that? Trivial solution and non-trivial solution, right? Trivial solution means x is just equal 0, and non-trivial solution case is x equal including x is equal to 0, and there are another possible solution, right? Then what does it mean? Because the solution can have just a single solution, or the infinitely many solution, or the no solution, right? So it means that non-trivial solutions will be the infinitely many solution. Then what does it mean? The linear dependence relation among the column vectors of the A will be the infinitely many possible equations. Okay, like this one. Okay. So this is the linear independence of the matrix columns. Therefore, the columns of the matrix A are linearly independent if and only if the matrix equation AX equals 0 has only trivial solution. So this is the exactly same what we have discussed so far, right? So if non-trivial if the non-homogeneous system X equals 0 has only trivial solution, like vector x equals 0, then the column of the matrix A are linearly independent. Okay, so here a question. So define if the following set of the vectors are linearly independent or not. Okay, so there's a two kinds of the problem. Okay, from the definition, we can say that a set of the two vectors v1 and v2 is linearly dependent if at least one of the vector is the multiple of the others. What does it mean? Okay, let's say V1 is the multiple of the V2. Let's say C times V2. Then in this case, we can represent this equation like vector V1 minus C times vector V2 is equal to 0, right? Right? Then, what does it mean? There exists the solution like the 1 and negative C transpose, like this, right? So what does it mean? Because there exists a non-trivial solution of this vector equation, we can say that vector V1 and V2 are linearly dependent. Okay. Okay. Let's see the example here. Okay. Okay. What is the vector V1? Okay, 1, 2, 3 here, and 1 here. This is the vector V1, right? Then what is the vector V2? 1, 2, 3, 4, 5, 6, and 1, 2. Something like this. So like this. So in this case, the vector V2 is the multiple of the vector V1. In other words, the vector V2 can be represented the 3 times vector V1. So it means that those vectors are linearly dependent. Okay. In other words, we can actually V3 is the meaning of the V3 can be replaced by the role of the vector V1. Okay, so we can say that this is the linearly dependent, right? Let's see another example. X1, X2. Okay, so yeah, just use the same figure. Yeah. Okay. What is the V1 is equal to 3, 2? 3, 2. Something like this. This is the V1 of the problem 2, right? Then this V1 and V2 have any scalar multiplication relationship. So in this case, they cannot be represent each other by the others, right? So in this case called the linearly independence, right? So yeah, this is just the case of the two vectors. Okay, what about the two or more vectors in the system? Here is the theorem characterization of the linearly dependent set. Okay, what does it mean? So this is the general. Yeah, this is the general case of the linear dependence set. Okay, let's say that there exists an indexed set of the S is equal to the V1 through the Vp of the two or more vector. So it means that P is equal to 1, right? Because of two or more vectors. So this set of the vectors is linearly dependent if and only if at least one of the vector in set S is a linear combination of the others. So in other words, at least one of the vectors in S is a linear combination of the others, then we can say that the set S is the linearly dependent. Okay? In other words, this set S is linearly dependent. Yeah, let's use the same color, linearly dependent. And if the V1 is not equal to 0, then some V1, where is the, let's say vector V1. Some V1 with the J is larger than 1 is a linear combination. Or linear combination of the preceding vectors. Like the V1 through the Vj minus 1. Okay? Yeah, let's prove this theorem. What does it mean? Okay, first of all, if some Vj in the set S is equal to the linear combination of the other vector, then Vj can be the subtracted from the both sides of the equation, then producing a linear dependent relation with a non-zero weight. What does it mean? Let's see the example. Okay, let's say V1 is equal to C2 V2 plus C2 V3. Okay. Then from the definition of the vector equation, we can represent this equation as a 0 is equal to negative 1 times V1 plus C2 times V2 plus C3 times V3 plus 0 times V4 plus 0 times Vp, like this. Because this term still here, but these terms are still 0, right? So what does it mean? There exists some solution like the C1 is equal to negative 1, C2 equals to C2, C3 is equal to C3, and C4 is equal to 0, something like that. So this is not a trivial solution, so this is a non-trivial solution. So we can say that because there exists a non-trivial solution, the set S is linearly dependent, right? Okay, so conversely, suppose the set S is the linearly dependent. Okay, so and then let's suppose the V1 is equal 0, then it is the trivial linear combination of the other vectors in S. What does it mean? If the vector V1 is 0, then it is the, where's that? Yeah. But the V1 is equal to 0, then it is the linear combination of other vectors in S. Let's see the detail. So first of all, vector V is not equal to 0, then there is some weight C1 through the Cp, which is not whole 0, then we can represent the vector equation C1 times V1 plus C2 times V2 plus Cp times Vp is equal to 0, right? Then let's suppose the J is the largest t is the subscript for the Cj is not non-zero, then and then j is equal to 1, the C1 times V1 is equal to 0, right? Why? Why? Because we suppose that the C2 from C2 to CP were 0, so in this case the C1 times V1 should be 0, but it's impossible. Why? Because V1 is not equal to 0, right? So we have to assume that the j is larger than 1, then we can represent the C1 times V1 plus blah 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 Cj times Vj plus the 0 times Vj plus 1 through the 0 times Vp, something like that, right? Because we assume that whole this coefficient was 0, right? Then what is the Vj from this equation? What is the Vj from the equation? By dividing the Cj from whole the other terms, Vj can be represented something like this. Okay. So what does it mean? So if the S is linearly dependent and V1 is not equal to 0, then some Vj is a linear combination of the preceding vector. So because this is the linear combination of the vector V1 through the Vj minus 1, so it is the proof of this theorem. Okay, so this is the theorem of the characterization of the linearly dependent set. Okay. Okay, so to recap, this theorem does not say that every vector in the linearly dependent set is the linear combination of the preceding vector. In other words, it not necessarily means that every vector can be represented as a linear combination of the preceding vector. Some vector or the arbitrary vector in a linearly dependent set may fail to be linear combination of the other vector. Okay, so what does it mean? If there is some vector, something like this, let's say this is the set S, then V1 maybe represent some kind of the linear combination of the other vector, but vector V2 may not be represented by the some kind of the vector V1 through the vector Vp, something like that. So it means that every vectors cannot be represented in the linear combination of the preceding vectors. Okay, so this is the property of this theorem. Okay, let's see the example. Okay, if we have the two vector u is equal to 3, 1, 0 and v is equal to 1, 6, 0, describe the set spanned by u and v. This is the first question, and explain why the vector w is in the span u, v if and only if the u, v, w is linearly dependent. It looks really complicated, right? So, okay, let's do this step by step. First of all, okay, what was the span? What was the span? What was the span? The span means that the whole possible linear combination of the vector u and v. Let's say the scalar c times vector u plus scalar t times vector v. Then c t are all kinds of the real values. So this is the span, right? Then first of all, the first question is to describe the set of the span by U and V. Then what is that? Then okay, so the vectors U, V are linearly independent. First of all, right? Because neither vector is the multiple of the other. What does it mean? This vector U and vector V cannot represent as each other. Like U cannot be the multiple times U, V, right? There's no scalar value C that's satisfying this equation, right? Or vector V cannot represent another scalar T, looks like that. So it means that U and V, vector U and V is linearly independent, so they can span the plane in the R3 domain, right? So span U, V is the xy plane with the x is equal to 0. Okay? Okay, let's see the figure first. Okay? Let's say because we are dealing with the R3 vector, right? So we can represent those vectors in the R3 space, something like this. So let's say those three axes are corresponding to the x1, x2, and x3. Then what is the U, vector U? Because vector U is equal to 3, 1, 0. So it means that x1 is 3, so x2 is 1, x3 is 0. So vector U should look like this, and because the V is 1, 6, 0, so let's say 1, then x2 is 1, 2, 3, 4, 5, 6, something like that. So vector V looks like this. So then what is the span of the U and V? So whole possible linear combination of the U vector U and V, so it will be the plane. Looks like this. Okay? So this is a span of the U vector U and V. Okay? So okay. So this is the first equation. The second equation was to explain why a vector W is in the span U, V if the U, V, W is linearly dependent. Okay? Okay, so let's say the vector U is the linear combination of the U and V. Then what is that? Then set U, V, W is the linearly dependent, right? Right? Why? From this theorem. The theorem was that if there exists at least one of the vector in S is a linear combination of the other, so we can say that this set is linearly dependent, right? So if the W is a linear combination of the U and V, for example, like the W is the C times vector U plus T times vector V, something like that, then we can say that set U, V, W is the linear dependent. Or suppose that the U, V, W is the linearly dependent. Okay, then what is that? The sum vector in this set should be linear combination of the preceding vector, right? So U or V or W is the linear combination of the preceding vector. However, vector U and vector V cannot be the linear combination of the preceding vector, right? Because of the this one, it was not a multiple of the others. Then vector U, in this case vector W, should be linear combination of the vector V and W. So it means that because the vector U and vector V cannot be the linear combination of the preceding vector, so vector V should be linear combination of the vector U and vector V, right? What does it mean? What does it mean? This is the exactly same equation of the span, right? So this is the exactly same equation of the span. So what does it mean? Vector W should be in span of the vector U and V. Okay, so we can conclude that the vector W is in the span U, V. So what is the reverse case? What is the reverse case? If W is not in the span U, V, then we can say that the set U, V, W is the linear independence. In this case, the vector W, it looks like that. It is not in the span of the vector U and V, right? But if the W is in the span U, V, then this U, V, W are linearly dependent, right? In other words, the vector W are in the span of the U, V. Okay? So, yeah. So, okay, this example generalized to any set of the U, V, W in R3 space with the U and the V linearly independent. So, to conclude that, we can conclude the set U, V, W will be the linearly dependent if and only if the W is in the plane spanned by U, V. So this is the case of this one. Okay. So if we go back to the question, explain why a vector W is in the span UV. UVW is linearly dependent. Okay, so it means that so if some vector in the set is represented by the span of the others, we can say that okay, that set is the linearly dependent. In other words, if some vector W is not represented by the span U, V, that it is called this set is the linearly independence case. Okay. So this is the definition of the linear independence and linearly independence case. Okay, here is the one more theorem, right? Actually, today is the several theorem. I guess to follow the proof of this theorem might be hard for you, so you don't necessarily follow every proof of the theorem, but please just remember what is the theorem and what's the meaning of that theorem. Okay. Okay, there is another theorem. If a set contains more vectors than if a set this looks like this, V1 through the Vp, contain more vectors, the number of vectors, then the number of entries in each vector, then the set is linearly dependent. What does it mean? In other words, okay, let's use the notation. Any set V1 through the Vp in the Rn space is the linearly dependent if number of the vectors is larger than the number of entry in the vector. Okay, what does it mean? Let's say we have a matrix A looks something like this, right? So we have a matrix A is equal to V1 through the Vp, looks like this. Then what is the size of this matrix? What is the size of the matrix? What is that? N by P. Why? Because there exists n columns with p. N rows and the p columns, right? So the size of the matrix A is the n by p, right? Then the equation of the Ax equals 0 is corresponds to the system of the n equation with a p unknown, right? N equation with a p unknown, right? So it means that we have to find the solution x1, x2 through the xp, right? Then if the p is larger than n, the shape of this matrix A looks like this. Blah 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 like this, right? In this case, there are more variables than the equation, right? So if we low reduce this original matrix, the shape of the echelon form will be looks like this, for example, right? So in this case, there must exist a free variable here, 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 right? This will be the in this case, this will be the base variable, and this will be the free variable. Anyway, there must exist a free variable. Then what does that mean? Those basic variable can be represented by those free variables. So there exists infinitely many solutions. So it means that their AX homogeneous system AX equals 0 has a non-trivial solution, and it means that the columns of the column vectors of the matrix A are linearly dependent because there is a non-trivial solution. Okay. So this is the one more theorem of today's lecture. This is the last theorem of today. Okay. So if a set S in the Rn space contain a zero vector, something like, okay, let's say V1, V2, zero vector through the Vp, something like that. Then this set is the linearly dependent. Why? If we renumber the vector like the 0, V1, V2 through the Vp, right? Then we can represent this set as a vector form like the C0 vector plus C2, let's say V1, C3, V3, let's say CP, VP is 0. Then what satisfies this equation? If C1, C3, CP is equal to 0 and C1 is not 0, let's say C1 is equal to 1, then this equation still satisfied. Why? Because there exists a non-zero vector here, right? So it means that there exists the non-trivial solution, right?